everyone. Welcome back to the next video of Antenna Enclave. So previous lectures we discussed basically about how exactly an antenna exists, what is the nature of its existing, how does a wave from a guided medium move into the unguided medium, that is from wire to the free space. So we all went through the sessions of opening the door, hence current goes to zero, the current has to turn back and go. When it is happening, there is total internal reflection since there is no impedance matching, and hence there is a small leakage of current which leads to radiation. So for me, then we also saw that for maximum power to be transferred, we had to have the impedance between the source and the load to be matched. So now, since I had to open the door, there comes a new structure which is called as antenna, because the structure is basically designed for a dimension for the frequency for which it is supposed to tune. Yeah. So when that happened, when we had to had a 50 ohm impedance matching, so antenna, it was also important that the impedance of the antenna also to be matched at 50 ohms. So we saw how we do that. So all we had to do was exactly design the antenna for that particular frequency. So when I do that, which means the antenna, the dimension of the antenna depends on the wavelength. So when I do that, the impedance gets automatically matched. So when the impedance are matched, I don't, there is a maximum power transfer happening. So radiation is more distance is covered, directivity is more, gain is more. So when I'm talking about these terms, gain, directivity, radiation and all, so let's get into the basic parameters which are involved in designing an antenna. So that's what we are going to see today. Okay, so let's discuss about what are the antenna parameters. I have a small question before we move into the parameters also. Is antenna passive or an active device? So what do you think, guys? Active and passive devices are passive device which needs external power to trigger. Active, self-activated, it doesn't need any external, it works on its own. So what do you think antenna is? Active or passive? Let's take if it was a active element, which means what? It's working on its own. So what kind of material do you choose for an antenna? Metals, right? So everything in this world, whatever metal we see, is it radiating or receiving something? Definitely no, right? Which means what? Any metal or anything, metal, it could be iron, steel, aluminium, gold, silver, can be made an antenna when I give power to it. Okay, antenna is basically a passive element, a simple passive element just lying down there. If I don't give power to it, it's just a dummy metal lying down there. So which means what? If I give power to any structure existing, will it act as antenna or not? What do you think, guys? It should, right? So as long as we know, it should work as a metal should work as antenna if I give power. But then again, what frequency will it catch? It will catch that frequency depending upon the dimension of it. Assume I take my earring itself. So this is, I mean, if I calculate the dimensions of it and give power to it, it will radiate at for the dimension for which it is mentioned for. So probably my earring here or my watch here. So every metal what we see, given a power to it, will definitely radiate or receive depending upon the size of these components. Okay, so probably we can start trying with a simple wire. Take a simple wire, give some power to it, and see if it is radiating or receiving something, anything like that. So probably in the next coming lectures, we'll definitely do that with something which is very handy to us. And how can I very easily check that if it can work as an antenna or not? We'll do that. Okay. So coming on to what are the basic parameters if I want to know, or if I want to know if I have to design the antenna is, first thing is frequency. Yeah. If I say please design an antenna, the first question which you would be asking is what is the frequency of it, right? Because the dimension depends on that. There are n number of other things which we need to know, like what is the radiation pattern? Do I need to have omnidirectional or directional? Okay. What is the polarization? What is the new word? Something called as radiation intensity, power density, directivity, gain, effective aperture, and radiation efficiency. So we'll see all these things one by one today. Okay. Coming on to what exactly is radiation pattern. So whatever I'm talking right now is reaching all direction, right? So this is like omnidirectional. So right now what I'm talking is going in all directions. So if assume I am an antenna, if I throw out energy, the receiver at any place surrounding me 360 degree, above me, below me, side, left, right, and all, can know the information. So this is omnidirectional antenna. So for example, we have considered an antenna which is directional, which means whatever I'm talking right now should reach in only one direction. Like in a simple example, the horse is put a shield there so that it focuses only on straight panel, right? So assume an antenna is throwing out energy only in one direction. So ideally, my radiation pattern should have been just one in one direction, correct? But practically what happens is, which it gives rise to some other unwanted lobes or unwanted information in other direction also. So the major lobe or the lobe which carries most of the information is called as major lobe. So my antenna would be exactly at the center here. So whatever it's throwing in directional pattern or direction in one direction, so it should have gone in this direction only. But practically what happens is just not the major lobe. I will get something called as back lobes also. So the lobe which is carrying major information is called as major lobe, and the lobe other than major lobe are called as minor lobes. Okay, in minor lobes we have two types. The one which is adjacent to major lobe are called side lobes. The one which is exactly opposite to it is called back lobe. Okay, and this is the maximum information I get here. So we are most concerned about this parameter. This is called as half power beam width. So what it says is wherein I get the maximum radiation. So I come 3 decibels down and find out the angle between this, that is half power points. So these two are my half power points. The angle which the radiation pattern is making at half power points is called half power beam width. Okay, this is a very important term when we are designing the directional antenna. So when you say, the first thing is frequency is fixed, and then you ask, do I need to design an omnidirectional antenna or a directional antenna? So if it's a directional antenna, then you would be asking how much will be the half power beam width, what should be the degree of it, how much should be the degree of it. So that's why it's very important. It says how much is it focused. Should it be 10 degree, should it be 20 degree, should it be 30 degree, the angle. So that decides how much precise or how much narrow my radiation pattern is. So this radiation pattern in definition, it's basically nothing but a graphical representation of radiation of an antenna as a function of direction, so which measures in terms of voltage per meter. Okay. Near the antenna, the intensity would be more. As I move along away from the antenna, the intensity would decrease. So few terms: major lobe, minor lobe, half power beam width, and the other few terms being. So assume I have a receiver exactly here wherein the radiation pattern is not reaching, though the receiver is very near to the transmitter, but my radiation is not covering that area. Hence I will not have any information there, or my radiation is, or my power thrown is not received by this person. So that those points are called as nulls. Okay, and these are my first nulls. So this is my maximum radiation pattern or major beam. So the angle which is made between the first null is called as beam width between first nulls. Okay, so this complete angle is called first null. So anywhere wherein the information is not being obtained is called as nulls. Okay, beam efficiency. So efficiency would have been 100% when I didn't have these minor lobes at all. These are unwanted lobes. When I throw out my information, my intention is it should not go anywhere else apart from my straightforward direction. So since it is going, my efficiency would definitely reduce, right? So beam efficiency decides about how much is the back lobe coming up. Had my complete area or complete radiation be covered in major lobe, my efficiency would have been 100%. It practically does not happen. There are n number of factors which affect it. We'll see one by one. Okay. So the next term which we need to know is, how does a radiation pattern look like? So what is the difference between isotropic and an omnidirectional antenna? Isotropic is what which puts out energy or radiates in all direction. So ideal case. Practically, none of the antenna gives us an isotropic radiation pattern. Okay, there will be a small dip exactly near the antenna axis. So we usually get a radiation pattern in a figure of 8 or something. So more or less, these omnidirectional antenna almost reach an isotropic, but definitely not an isotropic. So practically, we call it as omnidirectional antenna. The best example for an omnidirectional antenna is a dipole antenna. Okay. So if I want a directional antenna, you go back and recall the waveguides. So I had two waveguides and I started flaring it, right? So more the flare to a dipole antenna, I get omnidirectional. So when would I get a directional? When I start flaring it. So this configuration is called as a horn antenna. So horn antenna is one such directional antenna. Even in the figure what we see here, so this is all I was supposed to get, major lobe. So but I'm getting what? Side lobes and so many back lobes. So unwanted things. There are a lot of research happening with the reduction of side lobe itself, with the reduction of this minor lobe itself. So if I want to see or picturize the same thing in animation form, isotropic, just the antenna radiating aram se in all direction. Whereas an omnidirectional, so look at this, this is exactly a dipole antenna. Switches toggles between the positive and negative charges, right? So when one toggle happens, one radiation is put out. So the radiation and in this direction is not there. So this is called as omnidirectional antenna. Directional, any antenna which is putting out in one particular direction is called as a directional antenna. Okay. So let's come on to what do you mean by polarization? In a very simple term, if anyone asks that is a polarized wave, the electric field or magnetic field are in this direction. So the only thing what we need to remember is polarization basically tells the orientation of signal. How exactly my signal is moving. It's moving, right? Electric fields are generated, magnetic fields are generated. How are they moving? These two are perpendicular to each other and to the and perpendicular to the direction of propagation. This is what we have learned from the previous sessions, right? But how are they traveling? In what way they are traveling? What is the orientation of these waves? So that's what polarization tells. So we have three different types: linear polarization, circular polarization, and elliptical polarization. So what do you mean by linear polarization is, so either electric field will go in vertical direction, okay, or it will go in horizontal direction, okay, like this. So either a vertical or a horizontal polarized signal is called as a linear polarized wave, which means what? The electric field would travel in one particular, you see the red lines here, it would be going in vertical direction, okay. So, and which means wave is going in this direction, okay. So this is my vertical polarized wave. How about horizontal polarized wave? The wave would be traveling in this direction, as in you see here, right? So it's in this direction, okay. So either vertical or horizontal. So what do you mean by circular is, either the wave can travel in right hand circular wave or in left hand circular. Okay, those are the two types. So circular is very good. So if we see here, so circular is what? The one wave moves like this, which means in a simple term, if I have to say, the one signal will be right hand circular polarized and the other one will be left hand circular polarized. Okay, so as we see here, see the waves are traveling, the electric fields are in horizontal direction, the other one will be in vertical direction. Yeah? So this is how the movement would go on. So coming to a circular polarized wave, so as we are seeing, it would either rotate in a right hand circular wave or in a left hand circular manner. So this is basically used in DTH probably. A simple way of giving you an example is, in earlier days we had these signals when we watch TV scrambled or something, right? The reason being, let's consider any two adjacent channels of our DTH. So since my house is crowded with kids too, so it's always the Cartoon Network which is going on. So let's assume Cartoon Network and Pogo are the two channels, adjacent channels. though they have different frequency bands and they have some guard band also so that they don't interfere. By the time it reaches from satellite to our DTH service, in the journey from there, it may happen that they both might interfere and the signal might get cancelled away. So that's when we used to get scrambled signal or something like that. So nowadays what's happening is one of the channel is circular polarized, other adjacent channel is left right hand circular polarized, the other one will be left hand circular polarized. Even this happens, no matter what distance they are traveling, they don't know each other. I mean, the one orientation of one channel is different, the orientation of other channel is different. They don't know how to interfere also, they don't know how to interact also. So there is no chance that these two can interfere, and there will be loss of communication or loss of information or loss of your visualization of the channel at all. So now what has happened, so vertical or linear polarized DTS service is now changed into a circular polarized signal. Okay. Either it would be circular, right hand circular polarized or left hand circular polarized. The other kind of polarization is elliptical polarization. So in a circular polarization, the start of the electric field and magnetic field will be at the same point, because the major axis and minor axis in a circle is the same, right? Radius being the same. But what happens when an ellipse, the major axis and the minor axis are of different length. So now what happens, the electric field and the magnetic field would be starting from a different angle, or there is a small gap. So when such happens, though, there is 100% notion that the interference would not happen at all. Elliptical is best one. So if I want a very simple applications, I'll easily go for a linear polarized way. Okay? Or depends on what your application. So first is what your point, fix the frequency, find out what kind of radiation pattern you want, and then find out what is the polarization you are expecting. If polarization is not mentioned at all, you simply take a linear polarized way. Okay, having known what is radiation pattern and what is the polarization and all, next term what comes in a picture is a beam area. Okay, so now radiation is put out, right? Directional or omnidirectional, we'll come back to it. For a directional only, so there is some coverage happening in one particular direction. Now I need to know how much is the area which is covered. Dis- Distance and everything comes one by one now. So I need to know how much has my antenna covered, what is the area covered. So very simple way of calculating this is, so what do we do? If I want to find out a huge quantity, I'll just find out a small infinitesimal area or an incremental area. Then what do I do? Completely surface integrate over the surface. Yeah, I would get the complete beam area. So now this is my coordinate system works on r, theta and phi. So r would be what is the distance it's covering, theta would be one direction, this is like this, and phi would be the horizontal direction. So these three things I need to remember. Okay. So how do I calculate the beam area? A simple example being, let's take a watermelon. Okay. How do I cut a watermelon? Assume there's a watermelon. On top of it, I just cut a square. Okay, and I need to assume exactly at the center is my antenna. So I need to go till the center and cut a hole and remove that cone. Okay, so that gives me the solid angle. Yeah, solid angle is what? So angle is just what two things are making, right? So now I'm not bothered about, it's just not just one angle, I have two angles involved here. Theta is there, phi is there. So now what happens when I cut open the square shape and penetrate till the origin and then take back the whole thing, what do I get there? I get a nice cone, right? So that gives me a complete solid angle. If I want to find out how much is the solid angle, so let's look into the diagram here. So whatever cut I have done here, a square cut, and I have gone deep till the origin. So this distance gives me R. Okay, so when I say that is the radiation pattern, so the till the watermelon coverage is my radiation pattern. So that till the origin I'm going. So this small area towards theta direction is d theta, and when we see this axis, the direction what it is making, or the small incremental area what it is making is d phi. It's just not d theta into d phi. Had I taken only the area on the top of the surface, it would have been d theta into d phi, right? But I'm not interested only in that. I'm interested in the complete area which is going till the origin. So what is that distance? R. So one distance is what? R into d theta. Yeah, because d theta is there, so that distance is r. The other one is d phi, and that particular distance is again r. But the distance between, or the inclination between theta and phi is different, right? So this is this and this have some angle disorientation or difference. So that I represented in terms of sine theta. So now it's simply as simple as, if I want to find out the area of a square, it's L into length into breadth. So that dimension what I have taken here, d theta into d phi. But it is with respect to the distance. So it is d theta into r into d phi. Yeah. But the angle between theta and phi is different. So that I will represent in terms of sine theta. So it's what? R into d theta, r into sine theta into d phi. Okay, so this is what I get it for a small incremental area. In that, the solid angle is nothing but sine theta into d theta into d phi. Okay, so if I want to write it in a precise way, it's r square into d omega. So this is a small incremental area I have got. If I want to find out the complete beam area, what do? Surface integrate it over the complete sphere. So it is theta complete coverage and phi complete coverage. So I'll get the beam area, which depends upon the surface integrate of the power into d omega. Okay. So this is my expression for beam area. So having known how to calculate the complete area of the radiation pattern which an antenna is covering, so next term what comes is, what is the radiation intensity? This is this is the only quantity in antenna world or something which is not dependent on the distance. Okay, so anything. So if I say I'm talking right now, if I say at 1 meter the power is so much, at 2 meter the power is so much, everywhere the distance matters. So radiation intensity, I'm not bothered about the distance. All it speaks about is what is the power at that unit solid angle. So if I calculate, if I cut open solid, I mean those kind of cones on a watermelon at every given position, all I need to do is calculate, know the power at that solid angle, I will get the radiation intensity. So that's what it simply speaks about. Okay, solid angle for a directional antenna, I don't know, depends upon how narrow it is or whatever. How about solid angle for a omnidirectional antenna? Sorry. So omnidirectional antenna is putting out in all direction, right? So my solid angle would be equal to 4 pi. Yeah. So when I recalculate or substitute here, so PR by 4 pi, PR being the power, and this is my solid angle. That's what the definition of radiation intensity says. So PR by 4 pi speaks about the radiation intensity from an omnidirectional antenna. Okay. So the complete power radiated. So now what I have radiation intensity in one particular direction for a given solid angle. So if I have solid angles so many and I calculate the complete radiation intensity in every given point, if I want to find out the power radiated by the antenna, all I need to do is again integrate it in over the surface of with the radiation intensity and solid angle. So when I say surface area, what does it depend upon? The theta, what I take this angle. So assume antenna is here. Now I'm bothered about 0 to pi, 0 to 180 degree only. So when I'm throwing out energy, I'm only bothered about what is happening in the forward direction. I'm not interested about the what is happening below the antenna. Okay. Hence the radiation covered by it is 0 to 180 degree. Whereas, how about this coverage? So, antenna is throwing out energy, which means this is completely covered. Hence, phi will be from 0 to 2 pi, whereas theta will be from 0 to pi. And this is my radiation intensity, and this is my solid angle. Okay. So, after radiation intensity, what we would need to know is what is the power density. Okay. So, power density is a factor which speaks about, as we see from the diagram there. So an antenna is throwing out energy with some power. So it's transmitting with some power. At any given point, if I want to calculate the power density, all I need to know is with what power is it throwing out and what is the distance at which I'm calculating the radiation intensity. So it basically says power density says PT, which is the power transmitted, divided by 4 pi into R square. So at any given point, I can calculate the density of the power if I know with what power is the antenna throwing out energy and what is the distance between those two. This is a new term here, GT, which speaks about what is the gain of an antenna. Okay, so the gain of an antenna we are discussing the next few slides. So I'll just come back to the power density in that time. If it is an omnidirectional antenna, the gain would be 1. So assuming that this is 1 for now, so power density depends upon is two factors: what power am I transmitting and what is the distance at which I'm calculating the power density. Okay. So after power density, there's some very important topic which comes, which I need to know if it is a directional antenna, is directivity. So directivity, what it basically says is, we just discussed what is a radiation intensity. What is the radiation intensity? Power per unit solid angle is my radiation intensity. If I calculate the ratio of maximum radiation intensity to the average radiation intensity, I get the directivity. Okay. What do you mean by maximum radiation intensity and average radiation intensity? Okay. Radiation intensity. Right now, what I am talking is reaching in all directions. So the intensity is spread out. Would I get a maximum radiation intensity or average? What do you think? What I'm talking right now is going in all directions. So intensity is like distributed. Yeah. So it's not concentrated or it's not confined. It's in all direction, right? So in such case, would I get maximum or average? It's average radiation intensity, right? Okay. When do I get average radiation intensity? When I am throwing in all direction, when my signal is reaching in all direction. So what is this reaching in all direction? It's an omnidirectional antenna, which means what? When do I have an average radiation intensity? Because of an omnidirectional antenna. So likewise, when do I have maximum radiation intensity? Through a directional antenna. Yeah. So which means what? The radiation intensity of a directional antenna to the radiation intensity of an omnidirectional antenna is what gives me a directivity. Okay. It's a dimensionless ratio which is always greater than or equal to 1. So when I take omnidirectional antenna, okay, the ratio of both becomes 1. The radiation intensity, if I am taking the U max also as a omnidirectional antenna, to the ratio of U average also a omnidirectional antenna, the ratio will be 1. So the directivity of an ideal omnidirectional or an isotropic antenna is always 1. Okay. How do I calculate this, or how do I relate this to whatever we have already studied previously? Is, so we know that U max is by a directional antenna and U average is by a omnidirectional antenna. For an omnidirectional antenna, radiation intensity is given by PR by 4 pi. Correct? So this, when I rearrange and take this ratio on above, so PR is what? If I want to calculate power, all I need to know is I need to have the surface integration of radiation intensity in all direction. Yeah, the same thing I have written here. So if I need to calculate the radiation intensity, so I will have to need to know the power in all direction. Okay, so once I know the radiation intensity, I can always calculate the power. So once I know power at every given point, so I can find out the complete power in the whole area. So what is this given by? So surface integral of power with respect to, or with respect to the solid angle, is nothing but my beam area. So this is a beam area. So directivity is nothing but 4 pi by omega A. Okay. So omega A, now what is a beam? What is it? It's a beam area. So the beam covered by an isotropic antenna or an omnidirectional antenna is what? It's 4 pi, right? Yeah. So directivity is again what? 1. So which basically says, if I consider an omnidirectional antenna, the directivity is 1. So any other antenna which we consider, a horn antenna, any other antenna which is not an omnidirectional antenna, will have a directivity more than 1. So now your point is, you have fixed the frequency. When you come to fix the radiation pattern, if someone says design a directional antenna, then you will ask what will be the directivity of it. Okay. So that, which easily says how much far would it move. See, as we are seeing here, right now what I am talking is confined, is in all direction, right? Isotropic one. So the information is going, or the energy is spreading out in all direction. If I confine myself and speak in a straight direction, my with the same pitch, the distance would have increased. Hence, this is my directivity. Okay, so this is, which means what, the distance would have increased. Yeah. So directivity for an omnidirectional antenna is 1. Any other antenna which we design on directional antenna will have a directivity more than 1. Okay, so this is the ideal case. So we are seeing some other figure here, right? Gain. So we'll see about that in the next slide. So what is gain? So far, what I spoke about directivity being a ratio of maximum radiation intensity to the average radiation intensity. If the value of directivity is 1 for an omnidirectional antenna, everything what we spoke is with respect to ideal case. So I've not considered any loss at all, right? Will I not have any loss? No, I will definitely have loss, right? So when I look into the losses, what will I have? I square loss, which is the thermal loss or ohmic losses. Cable joints, when I'm transmitting from wire to wireless, maybe there is some loss in the cable. Anything, worn out eventually. Or if I have a long cable which I have joined and made a big cable, so even in that time I will have a number of losses. So when I consider all these losses, my gain expression will be equal to k into d. Okay, so gain is basically a relative term in which the actual antenna is compared to a reference antenna. Now my reference antenna is what? Directivity of an omnidirectional, which is an ideal case. So keeping that in mind, if I design an antenna, how well the gain will match to directivity. If assume K, which is the antenna efficiency, be 1 or 100%, what will be gain? Exactly equal to directivity. So ideally, directivity is my very well known factor. But when I'm practically designing it, gain comes into picture because the transmitted antenna to the radiated antenna may not be same. No matter how much I talk about impedance matching, in simulation, yes, we can make sure that we get 50 ohms. Then comes fabrication losses, these I square R loss, joint loss, cable losses. With all these things, with what power I'm transmitting, might not be radiated out in out or free space, right? So when that happens, K will not be 100%, it would be less than that. Or I can also speak of antenna efficiency with respect to this expression, where RR being radiation resistance and RL being loss resistance. If I design my antenna to have only radiation resistance, then again my K will be 1, assuming loss resistance is 0. Okay, this doesn't happen practically. Hence, the efficiency would not be 100%, less than that, and gain also reduces. So previously when we look into this graph, directivity is my ideal case, but in practical scenario, what happens, due to considering all the losses and all, my radiation or the coverage would reduce. So gain gives us a practical picture of what is happening. Okay, and one more very important term which we need to know for today's session is effective aperture of the antenna. Okay, so what it basically means. So aperture is what you have seen a horn antenna. So assuming I have an horn, this is a waveguide, a simple waveguide which is flared out. Why do I flare out? Recall. So more the time for the current to turn back and go, more will be the leakage current and hence more radiation. Hence we start tapering, right? So this is my horn antenna. Okay. So this is a complete actual size. So in practical scenario, what happens is, due to the direction of the wave which is hitting, so assuming this horn antenna, what I'm considering is a receiving antenna. The fields might come in this direction, in this direction, in this direction, any direction, I don't know. Okay. Not the complete antenna aperture would be involved in radiation. So assume if the field is falling in this direction, so this part is completely covered, right? I wouldn't get radiation in that direction. I mean, it wouldn't hit there at all. So that part or that area of the antenna which gets involved in radiation is called as effective aperture. Okay, if the complete physical aperture gets involved in radiation, the complete area will be, area of the antenna will be effective aperture. But practically, it may not happen. Hence, we define that an actual area which gets involved in radiation is called as effective area. Okay, which depends upon this expression. power radiated to the power density at that given point. So which means what? If I say effective area, if I recalculate the equivalent circuit of the antenna and analyze it, what happens is effective aperture is just that concept wherein all the actual area being involved in the radiation. Here I'm not talking about the impedance matching also. So in when I calculate the equivalent circuit, it will be ZA. So ZA involves what? Radiation, so resistance and reactance part also of an antenna. So if I want maximum effective aperture, okay, effective aperture is only physical quantity or physical area which is getting involved. So if I find out the area of that antenna and write the equivalent circuit, it will be ZA. So this ZA is nothing but which involves both resistance and reactance. So do I need reactance part? How much is my impedance for matching? It's 50 ohms plus or minus J0, right? Which means that reactance part has to go to 0. When that also goes to 0 and I have effective aperture, now this effective aperture will be maximum effective aperture. Okay, so this term AEM, which is what? My effective aperture which is involved in radiation, along with it the impedance of it is pure resistive. So then I get, then that is what is my ideal case, right? Impedance is perfectly matched and whatever area is getting involved in radiation, I am considering that. So this gives me the directivity. Okay, what is the relation between gain and directivity with respect to aperture? When I'm taking the ideal case, which is directivity, I get maximum effective aperture. When I consider the practical case, I only consider the effective aperture. In this, since there are n number of losses, maybe the antenna is not perfectly matched to the source impedance. It may not be exactly 50 ohms, maybe some reactance part is involved in it. So when all these things are involved in a practical scenario, I consider gain. In an ideal scenario, it's maximum effective aperture, 50 ohms, perfectly done. Effective aperture, I have taken into consideration. So this relation between directivity to the effective aperture also is very important in our antenna world. Okay. So if I want to summarize the same thing, what we studied in today's session was, we started with antenna. If I want to design an antenna, what I need to know is the frequency. Second thing is, if I want to have a directional antenna or a omnidirectional antenna. So if I want to have an omnidirectional antenna, I know its radiation is put out in all direction. Directivity would and gain in would be 1. Okay. If I am designing a directional antenna, what I need to know is how much should be the directivity. Yeah. And probably we'll also need to ask how much should be the half power beamwidth. If I know half power beamwidth, there's an expression which gives the relation between half power beamwidths to the beam area. So in the next session, we will find out what is the relation of beam area to the directivity. So we already studied that directivity is equal to 4 pi by omega A, right? So there is also a relation between half power beamwidth to directivity. Okay, once I know that, if someone says you design a directional antenna, or they don't have to specify directional antenna also, design an antenna at this given frequency which is having a half power beamwidth of 20 degree. So I can come back and calculate what is the directivity. So I would know through calculations how much should be the directivity and everything. Okay, so then I can decide upon what kind of shape of the antenna do I need to choose. So how much directivity is there, depending on that the shape of the antenna will be discussed. So in the next coming sessions we will see, or we will exactly get into the equation part of the relation between whatever we have discussed over. This session was only to give you a definition of what these terms are, the relation between these two, how exactly would I use this to calculate lot of other things in antenna, and then subsequently we'll discuss about how do I choose the shape. Size is important for a given frequency, but how do I choose the shape? Yeah, so we'll see all those things in the next coming sessions. So if you like this video, if you have understood any concept of this, please like, comment and subscribe for the channel Antenna Enclave. Okay. Thank you so much.